Okay, so let's get started. We are almost done with Chapter 3. There's a few little short sections, and there's some sort of things that I want to tell you as part of this that try to tie the industry and career together with what we're learning maybe a little bit more. First of all, does everybody know what X86 even means? Do you guys even know where we get this phrase that we keep using all the time, X86? Yes? Yep. Yeah. A few generations before that, Intel created the set of assembly language instructions that make up the vocabulary that we can still program in today. You know, like move and add and div and fdiv and all that junk. Right? So they document all that. They built a chip in the 70s to do this stuff, and I think it was the 70s. It could have been the 80s, but I don't think so. And you know, it's so easy to go look up. I don't know why I'm so lazy, but I think they started this. And chips then all had fantastically easy to remember model numbers like 64003 and you know B8289. And so Intel said, "Oh, okay, we'll play this," and they came out with one called the 80. It's easier if I don't use a highlighter, huh? Do a pen, maybe with a color. They came out with the one that was the 8086, and it was for microprocessors, very scaled down, very less expensive, not all that fast, cheap enough that IBM chose to build a PC out of it. And the rest is history. So the programming language, the assembly language commands that 8086 that Intel implemented in here sort of set a mark in stone that was the starting point for this growth that we've seen. And they came out with an 8286 and then a 386 and a 486 that he mentioned, and they stopped using the numbers eventually, and they started using names like Pentium and Pro Pentium and Pentium 2 and Westmere and Xeon and on and on and on. Now it's like an alphabet soup of names. But we still call it x86 because it's the same assembly language commands. We've added to them dramatically over time. In fact, with every new increase in chips, they've added about 30 new commands, I think. So there's over 900 now. Good luck writing the compiler to pick which of 900 commands you want to use, especially if you're trying to write one that uses all of them. But the reason why there's 900 isn't just because there's 900 different things we want to do. A big piece of it is because we need programs that were compiled and made into executable code and ran on 8086 chips to also run on the very newest Intel x86-based platform today. Because if somebody wrote a program 50 years ago that runs on, and it's not quite that long that the PC came out. It came out like in 81, I think. If they wrote a program that's compiled on there, there's no reason to throw the program away if it's still useful. It could be embedded in something like controlling when to turn a water pump on at a water treatment plant, or detecting a high level under a bridge, or when to close a crossing arm, or the mixture of fuel and gas in something, you know, whatever. There are millions of systems. Intel makes chips for laptops and servers, but there's millions of their chips in what are called embedded systems that we learned about on like the very first day of class, where it doesn't look like a PC and you can't get there. So it's still the case that if that piece of hardware dies, you can replace it with a new one and it will still run the same old commands with the same type of register references and the same 16-bit architecture or 8-bit architecture. That stuff will still work because Intel doesn't want to force you off onto a different platform. And I guarantee you that if you work for a big company or interact with one, you will find forever examples of very critical systems that these businesses operate that are running on a computer that's not made anymore, that's written in code that the source code has been lost for 25 years, and the original author died after he retired 25 years ago, and no one has any idea how it works. They know exactly what it does. And they could hire someone to rewrite it from scratch again, but it's a huge pain, and why fix it if it ain't broke? Right? So I guarantee you'll be shocked that this exists. So I can give you as an example the system that the government of Mexico uses to issue customs receipts when you pay to import and export. It's like the third biggest source of income for the economy, and it runs on systems where it's exactly the example I just gave you. Old 25-year-old IBM PCs. Nobody touch it. Don't ever turn it off. It may not turn back on again. I mean, it's one of those situations, and it is very, very common. The lottery system of the state of Texas, the network that it runs on, exactly the same thing. When I told those guys before I left, if it blows up, there's going to be hell to pay. This on schools. You guys are not ready for the political fallout. You need to replace it. And they didn't want to do it, and I said, okay, well, my part's done. I told you in writing you needed to do it, and here's why. So, congratulations on a brilliant but short career if it happens, because you will all lose your jobs if that takes place. So it just happens all the time, and it's a little shocking. There's a big industry, and it used to be huge 5 years ago, bigger than maybe it is now, called RISC to x86 migration, where if you wrote your code to run on an IBM AIX system, which used a totally different type of concept of a chip, like ARM, where it's got a very reduced number of instructions. It's thought to be much simpler to program. You do not have all these fancy multimedia commands and things to do vector multiplication and Fibonacci series and fast Fourier transforms. You just have basic nuts and bolts. But the thought is that you can make the CPU so much faster by getting rid of those slope things that even though a compiler is going to have to write like 1 million lines of code every time you want to do a fast Fourier transform, whereas on an Intel chip it's a single command, so it's 1 line of code, and it's going to take longer, that's so rare that you're going to be better off. So there's 2 schools of thought, and Intel has won that war in business for the most part. So most servers are Intel-based, like the super vast majority, 99% plus. So people that wrote all these systems to run on these IBM boxes want to get them off of that and onto x86. Why? What's wrong with it? Why move? Well, if it's an area of active development, like it was for Kohl's stores, Kohl's, the department stores, they were my customers. They were having a harder time finding programmers. They couldn't go to colleges and hire recent grads that knew how to program and this stuff because nobody was teaching it. And there were lots more people making x86 machines, including the Chinese, which were doing that to the pricing because they're really good at finding the efficiencies. And you weren't seeing any of that on RISC-based systems. And so if you want to lower your cost profile and continue to buy servers, you definitely want to be on that slope, not on that slope. So you are going to pay to move everything over. So there's a company in Chicago that we work with that has like 20,000 employees, a lot of them contract around the world, and they will port your code. So it's really expensive. Cold spent, I don't know, more than $10 million maybe. I know $7 million in the first round to kind of do this stuff. So it's a big deal. I had another customer, Fiserv. They run the software that a bank would need to do like your statements and to look at your online balance and allow you to do a online bill pay and to handle deposits and all of that kind of junk that banks need to do. And if you're a small bank, instead of buying a big system and running a data center, like who wants to do that? By the way, I've never met a CFO at any size company in my life that if you could show them a way where they could dump their data center off of the end of a barge into the bottom of the ocean, they wouldn't do it in a heartbeat. The CFO and the CIO are usually like that, because the CFO views the CIO as an endless, bottomless pit of money sucking out of the budget. Looking me in the eye, the CFO is like, I poured $200 million down that hole's neck last year, and if I could figure out how to stop doing it tomorrow, I'd fire him in a heartbeat. But I can't. He runs our business. So don't think that just because you're in computing that the CFO loves you. They hate your guts. You're really expensive. And so this Fiserv business provided a huge solution long before cloud was big by telling these small bankers, you don't need to do any of that stuff. Just pay us a small amount per account, per month, and we'll do everything. You got 1,000 accounts, it's $2 a month each, that's $2,000. Like, are you kidding? So it was a drink, consumption-based model for years, and they were very successful. They had a Unisys mainframe, and the mainframe was no longer being made. The code worked great, so they had three choices. They can either hire Ernst & Young or somebody else to come in and figure out all the business processes that code was doing. Like, was it issuing the treasury statements that have to be filed with the Federal Reserve every night showing the ratio of your deposits in hand to your loans? Or was it doing all that kind of junk? So you could pay them to sort of figure that out, rewrite new specifications, hire a firm to code it, and they will often bid on that as well, but you could find IBM or somebody. So totally rewrite it from ground up. That's one alternative. Another thing you could do is hire this company to port your code, if you have it, if you have the source code, which you may not. And they took a third route, which was really clever. And have you guys ever heard of people running Windows on a Mac or vice versa? So one of the ways you do it is with VirtualBox or VMware Fusion, or you run a program and you put, let's say, Windows on top of it. You can even run Windows on top of Windows. I do that. So I have multiple versions of Windows all running on Windows 10. And this thing walks and talks like an Intel x86-based machine. It's so convincing that when you load an operating system on top of it, the operating system can't tell that it's not on an actual x86 machine. It sees everything, a keyboard and a mouse and a network card and storage and on and on and on. So they found a version of this Unisys mainframe in a virtual machine, and they ran it on a new x86 server. So they ran x86, and on top of it they ran this Unisys emulator. It was a program, and then they just moved all their Unisys programs on top of it, and they thought they were still on a mainframe, and the things worked. So you can get clever with this stuff, but this is why learning a little bit of assembly will pay off, because it's very high odds that you will run into pieces of it, or you'll at least need to know kind of what's going on or how things work, because virtual machines totally dominate the vast majority of servers. 80% plus of applications are running in a virtual machine environment, which means they're running on a physical Intel server, but they're running on an operating system that's one of 10 other operating systems that are also running at the same time on that server. Every single operating system thinks it's the only operating system running. And they may be all Windows 10, but for different customers, for example. So that's how Dropbox, all the stuff you use that's in the cloud, that's how all of it is run. That's dominant, yes. They share all the physical hardware, but they isolate it logically so that there's no chance, people believe, of ever being exposed to someone else's memory. And there are protections that Intel has built for the last 10 years or so in the hardware itself. They came up with this concept of segments. So they can isolate you into a segment, and the hardware will enforce that no address request that fits within that segment will be honored if it's not coming from within the segment. And if you do, you have a segmentation fault, if you've ever seen that error on a PC or on a server, for example. So the hardware's had to do things as well to kind of help. So Intel's absolutely modified their chips to support this VM environment, but that's the way almost everything runs. The exceptions are things that are so delay intolerant and so performance strict that they can't even afford to share CPU cycles with an operating system. So they will put their program directly on the hardware. You don't have to have an operating system. It's just a program. An operating system is nothing other than a program, and you write your program on top of that program. but you can write a program directly on the hardware if you want. So database systems do that. Oracle, financials, those things they run on what's called bare metal. That's called bare metal mode, where you do not have an operating system, you do not have virtual machines. They take it from the ground up. They need every single CPU cycle they can get, because they're running millions of financial transactions a second. All right, so Fiserv, back to them. We got that Unisys emulator, and they were able to continue to march forward. So that's a long way of kind of getting back to x86, which does dominate the industry. There's 2 companies that make x86-based chips that are large. I've learned from students this semester that the Chinese and the Russians are also manufacturing some. I knew about the Russians, but the 2 big firms are Intel and, anybody know the other one? AMD. AMD first came up with these multimedia extensions that I'll chat about for a minute. But it makes sense because they're deep into graphics. They do ATI Radeon cards and all of that kind of stuff. There's a good chance that the graphics card in your system is built by NVIDIA or by AMD. All right, so what are these MMX instructions? They're a class of instructions that implement subword parallelism, but they also are known, I don't know why it does this sometimes, they're also used for performing the same operation on a big stream of data. So MMX came out when laptop makers figured out that, or believed that it was now possible, they could now convince you to buy another laptop a little sooner than you were planning if they put a camera and a microphone in the laptop, instead of making you buy one and clip it on and run a USB cable and all that junk that we used to do. It was going to be expensive, but they thought they could make it up, right? So it was worth doing it. But they needed support from Intel because it was a pain to write code to deal with it. So there's lots of standards for how to take raw data coming in from a microphone and turn it into a format that's suitable to be stored or transmitted. So for example, if you're making a DVD and it's a good quality microphone, I mean, those Intel chips run those systems too, then you want to capture at a certain rate. You want to use lossless compression, so you don't lose any data, because it's going to go on a Blu-ray DVD, and it's got to be Dolby qualified and all that. On the other hand, if what the microphone is capturing is something for a dial-up Skype call, you know, with a dial-up modem, talk about antique, then it's got to compress dramatically the data, and there's a standard number for that. So you've heard of JPEG and MPEG. Those are names of standards groups. Joint Photographic Experts Group, Motion Pictures Experts Group. They publish standards. G.711 is a standard that tells you exactly how many bits per second, the packet size, the type of compression, the various levels for each frequency, on all of that stuff. Who wants to have to learn all that? There's hundreds of them to be able to write code to use this new microphone and camera in your new fancy laptop. So Intel deployed, I think it was AMD first, like I said, these new assembly language commands that you tell it the source, like here's the stack of registers, and you'd tell it the format by putting into a register, maybe the next 5 bits would be one of 32 different compression standards you want to use, and it would just produce it and put the results in memory. And then you could put them in an Ethernet frame and send them out, or you could write them into RAM, or you could put them on a hard drive, or play it back over speakers, or whatever it is you're trying to do with it. Much, much easier. It gets lots more people interested in writing programs to do that stuff. And so they can actually accelerate the market if they are smart and pick a popular set of new instructions. That ended up being scalar or streaming instructions. So all these things basically take a whole long list. So if you use an instruction like add, you've got to tell it the 2 locations to add, this one and this one to that one. If you use sort of a vector scalar add, I'm making up a new instruction name, but you'll see letters like this, then it's going to be expecting everything to be in this specific stack of registers. It's expecting there to be 32 of them, and it's expecting you to give it a location where it's going to put the results. One command instead of 32 different commands with loads and stores to follow. So they can speed that stuff up dramatically. That's essentially doing the same thing to lots of pieces of data at once, and that's what GPUs are really good at doing as well. So you can hand it a million pixels, and you want to change the position of a light in your video game. somebody turns the light on in a room. So now for every one of those pixels, you've got to decide based on the angle, the distance, and the reflectivity, does the pixel become brighter or darker or no change, and if so, by how much? Does it change the color at all? Is there now something illuminated that's blue in front of it that reflects blue, and now it's going to turn a little bit bluish? So it's the same calculation on every single one of those pixels. GPUs scream at doing that. It's the same kind of concept. All right. We've looked at enough of those. There's some examples of a few commands in here. Another way these things kind of help us with subword parallelism, which again is the topic of this part of the chapter. I got to zoom this thing back up here, because I end up scrolling up and it shrinks it when I'm in the wrong window. Almost there. Last lecture, I just quit the program and started it up again. I got kind of tired of doing it. So here's a pretty popular algorithm called DGEM, Double Precision General Matrix Multiply. And if you've done matrix multiplication, it's tedious. There's thousands of steps. You take the first row and you multiply by every column of the second matrix and you record the value cell by cell. Then you go to the next row and you multiply by every column. So if these are 1,000 by 1,000 matrices or even bigger, it takes a while. There are 3 loops, lots of code. Or you could just write a single assembly language command, because Intel does DGEM with a single command. You point it to the matrices and turn it loose. And if a compiler author worked with Intel, which they do, then not only will they convert that to a single command and it'll run faster because it's on hardware, but it'll also run much faster than it might for you for another reason, and that's because they'll notice that the matrix from which you're getting the row, against which you're multiplying all the columns in the next one, it's too big to fit in the amount of cache memory that you've been allocated. So instead of trying to do the whole row, they'll just do half of it. Because if you think about it, this row is going to be very popular. It's going to be used to multiply in this column, and then this column, and then this one, and this one, and this one. So do not set me up to have to go to RAM every time and get it. It's the same row. Put it in fast memory, leave it there, and I can remove all those I/O waits that my CPU would be stalled waiting on otherwise. So a good compiler will know and will only feed this single magical instruction as many of these cells at a time, because you can multiply these matrices in parallel and in blocks and all kinds of ways. So you can speed up calculating the answer by using that hardware instruction intelligently, not just using the hardware instruction. So this is just run circles around the way we've done it. I mean, we're talking 1 million times faster, like 1 millionth or 100,000 times faster. So you can get 100,000-fold increases sometimes in your career if you're lucky. SAP had a site called the 100,000 Club of customers that had sped up the time it took to produce a business report on how their sales were doing 100,000-fold by upgrading to solid state completely. It's very expensive, but if you can tell a CFO, I can show you how your stores are doing every 5 minutes instead of once a day, they're like, where do I sign? If you want to know every 5 minutes what's selling across all Kroger stores, and it did that discount program work? If so, immediately copy it to the other 800 stores. Right now, put it into the system, change the price. Here's the MP3 file, play the announcement over the speakers. Every 6 minutes for the next hour, it's going like crazy in the 80 test stores. And that stuff happens live. Target, they follow you in the store if you use the Cartwheel app, and they know how long you spend at things. And if they see, then they compare your basket and they see you buy those two things, expect soon, if a few other people do it, that they'll be next to each other in the store. They'll cut the time you waste walking to the other end, and they will move that product next to the other one you buy. If you always buy batteries and chips, they'll put batteries next to chips for you, right? Because it's got to be easier than Amazon or you're not going to do it, and they know it. So there's crazy improvements that we are always trying to grab in these systems as we go through it, and Intel has a big role to play here. So DGEM is an example. Here's an example of one of these command names. Okay, we'll skip through a little bit. There's only a couple of questions in here. That's easy, and we're ready to get to the next one, if I can just find where they put it. Here it is, fallacies and pitfalls. So the homework has a couple of fun problems. One of them shows the second thing I'll talk about, but first, shifting left multiplies by 2 perfectly, shifting right doesn't divide by 2 perfectly. So they walk you through a little bit of example to show you that. These are actually quite interesting. They're sort of parlor tricks. There's a floating point. One floating point turns out is not associative. So what they're basically saying is if you have A plus B plus C, if you do A plus B plus C or A plus B plus C, you will get different answers from the CPU you are using on your laptop today. I can guarantee it if it's floating point, because we've already seen how it's really hard to represent floating point accurately. So I give you a problem. It's a pretty famous problem, but I built a Google sheet out of it so everyone can do it. It's, say you borrow 25 bucks from mom, and in 5 chores that you do, you know, I'm making up numbers. This isn't going to add up to 25, but I'm just showing you the types of numbers. When you do this in the Google sheet, these add up to 25. So you hope you pay back your debt to mom. You will not get 0 as the answer. Intel cannot add a positive and a negative 25 together and get 0. Not if you do it this way. And then I have you do it sort of a single sum command. Then I have you do the first 2 in one sum and the other 3 in one. And then I have you do the first 3 in one and the last 3 in one. You'll get different answers for some of those. Depends on the version of Excel or Google Sheets, depends on the Intel chip that you have, how they implemented floating point. But it's a big eye-opener. It doesn't have to be a crazy number like 1.0000001 times 10 to the minus 120. No, 25 will do it. It's good enough. So I show you some examples. Also give you an online C compiler where you can type in a couple of commands and see how the hardware returns back specific floating point combinations that are not recognized as numbers, and you will see in the output that it tells you it's infinity, or it's not a number, or it's something like that. So I'll give you a math problem, and I'll have you add something to it, and when you add it, even though it can be represented, it's not permitted in IEEE 754 because the bit combination is a reserved one. So if you're unlucky and your math problem has that as an answer, well, it's never going to be represented on any computer on Earth today that uses 754 because that answer has been removed from circulation. And that answer means somebody else did something that's resulted in positive or negative infinity. So it shows you what we talked about with those special values. So I walk you through that. So that should be fun to go through as a homework. And I wrote them for you guys this year, so they're new. Something else that you don't want to believe is that only theoretical mathematicians care about floating point accuracy. We talked about the big Intel FDiv bug. This was a headline, IBM to stop shipping Pentium PCs. That's when the CEO of Intel, you know, considers like his life still worth living or not, or something, you know, crazy. You do not want to see that headline if you're the head of Intel. They blew it on that. They recovered though, and they mea culpa, and they marched ahead. So you can recover from things like that. But you know, when your mom calls and asks you like, what's up with this Intel stuff, you know that it's out there. I still remember the day when my mom told me she got an email address. And I had this feeling like, you're playing in my sandbox with my toys. What are you doing? Oh, I got an email address on AOL. Okay, well, at least it's AOL. So it's not a real, you know. All right, so a couple of concluding remarks in here. There's more commands that you can look at. There's, you know, some things that show you sort of the ratio of how many of our commands are integer versus others. There's a historical section. You need to wrap up Section 3. I'll give you to the weekend, but we're now done with Chapter 3. All right? So marching on to Chapter 4, what this is going to get us is a introduction to what's called a data path, which is going to show us how to physically organize elements together on a chip where we can pass our signals through and get results out, but implement pipelining. So if you don't organize your laundromat to give room for more than one person in there like you would at home, then only one person can use them. If you say, like, I'm using the laundry room. Well, I need to wash some clothes. Well, then you need to wait until I'm done. But you're not using the washer anymore. Yeah, but there's only room in here for one person. You need to wait until I'm done, and then you can come back and use the laundry room. I'm using it now. That's non-pipeline. At a washateria, that would never work. You empty out a washer. There's not a pair. You get them one at a time. When you leave the washer, somebody else can use it. They don't care if you're drying your clothes. There's nothing. That's pipeline. Most things we do are pipeline. At the airport, the security agent decides who to call next to the front. That's pipelining. An assembly line, manufacturing cars, all those kinds of examples are pipelining. So we need to preserve that, and it requires careful design in a data path. So we're going to look at some examples, but we're only going to use a subset of MIPS commands. We'll use load and store word. We'll use add and subtract, and or, set on less than, and then branch, equal, and jump. And that's it. We're not going to use any other commands, because these are good proxies for all the other math commands. These are good proxies for all the other logical commands. This is good enough for all the other branches and so forth. They're going to pass through the same elements in the CPU. Those other details are just flavors. All right, so let's see if we can remember kind of how things work. And I got to kneel down so I can get a little closer and read here carefully. The first step in running a command in MIPS through a chip is which. What's the first thing you need to do? Use the ALU for operations, for address calculation, for comparisons, read the registers, or fetch the instruction from memory. First thing you need to do is what you're supposed to do. So you're going to fetch an instruction from memory. And once you have the instruction, you can see what the instruction is. All MIPS instructions, except for jumps, use registers. So if you're going to need to do comparisons or math, you need to know on what. You can have some immediates, but the rest of the commands, there's at least one register in there, right? So we need to read the registers. If it's a memory reference instruction like a load word or a store word, then you need to calculate an address, like store word at 12 bytes past the start of the array in S0 and get me that, put this answer there. If it's arithmetic logic, then you're going to use an ALU to do an operation. And if it's branches, then you're going to be doing comparison. Branch on equal. Is this equal to that? Yes or no. Is this greater than that? Yes or no. Is it less than that? Those are comparisons. Right, so those are kind of the things that we need to implement in our data path. So we start with this diagram, and what this starts us off with is down the road. Oh, somebody is not muted out there. Well, everybody should be muted, so if they're not muted, let me see if we can get it again. Thank you for telling me. Sorry you had to type it in uppercase before I saw it. That's usually not good. All right. Yeah, that's not totally on him. Apparently when I stopped the first lecture, I turned off the mute on entry. So that's actually my bad. Isn't it always? Has it ever not been my bad? Okay, so here's a diagram called a data path. What we see is a program counter. The program counter is a register, 32 bits. What does it contain? What does that mean, the number of the instruction? So the name is a hint, counter. So you will use it to get an instruction, that's for sure. The instruction actually comes out of a special area of RAM reserved for instructions. But how do you know which one to go get? The PC contains the address in instruction memory where you will find that 32 bits. So the program counter spends its time incrementing, because usually we run one line of code and then the next, and the next, and the next, right? So the thing that we normally want the program counter to do is give us that address so we can go into instruction memory and find the instruction, and then add 4. So we're going to have a little toy adder here. All it does is add 4 and put the answer back in the program counter. Now it points to the next address. So when it's time to go get the next one, it has the next address, and then it's going to just continue that infinitely. That's what the program counter does forever, until you divert it with a branch or a jump. And if you do that, then you calculate for a branch, for example, if you want a branch, if not equal, down to L1, you remember we used L1 a lot in sample code, and let's say that's 9 more lines down in your assembly language code, then the compiler will turn that branch to L1 to add 9 to the program counter when you get here, if the branch is true. And so that's another adder, where you're going to, well, it'll add the right number of bytes, but it will be bytes. But I'm just trying to keep it a little higher level for the moment. PC is a full 32-bit address in memory, so it is a byte-level address. The last 2 bits are always going to be 0, so it points to the beginning of a word, but it's the whole thing. So when you need to go 9 more lines of instruction down to reach that L1, then it's 36 bytes, 9 words, but the system is storing that delta, and it's adding it to the PC. And that's where it's going to set it. So you're either going to use this one, or the output here, or you're going to use the output here. And remember, those immediates can be negative. So you could say branch up to L1. It doesn't have to be below you. It can be above you. And then it's a negative number you're going to subtract from the program counter and set it up back up to a higher line of code to run again. Yeah. So presumably it'll, you change the address in the program counter. It will reload an instruction. Presumably it's run before, because it sounds like this branch is at the end of a loop. Lots of times we write them at the beginning, but this one's at the end, so it'll be jumping up with a negative number every time. At some point, you're going to reach some condition where the branch test will fail, and it will not execute that branch. It'll just go to the next line of code. It'll fall out of the loop in that example, in that case. Okay, you've got instruction memory. One of the things that's important to keep in mind that's a little bit of a surprise, it's not obvious, we haven't talked about it a whole lot, all RAM on all systems that you use, from your phone to your tablet to your laptop, have memory split into 2 parts. And some of it is reserved for the machine language code of the instructions, and it's called instruction memory. And that's all it has, are instructions. So all the executable lines of code for all the programs that are running in your PC at any given time, whatever parts of Excel and Word are being used, not the data, the program itself, all those lines of code come from this single block of instruction memory. So you might have some Excel in here, you might have some Word up here, you know, etc. But it's all here. So therefore, obviously, you can't load all of your programs all at once. You try to load the next lines of code that you think you're going to need. So the system's constantly trying to guess. Okay, up here is data memory. And you can access instruction memory and data memory simultaneously. So it's like 2 blocks of RAM, but it's one system. You're only plugging in one set of DIMM cards in your laptop, and it's being split by the system into instruction and data memory. RAM doesn't really, you know, it's used to this. This is the way it works. It overcomes a fundamental dilemma, which is we're using the same memory to store both. I mean, it is the same block of RAM overall. So if you're using the same memory to store both, and you can only do one thing at a time. First, you'll go and get the instruction, and then you'll go and get the contents of the numbers you're supposed to multiply. And then you'll get the next instruction, and then you'll go and store something in the memory, and then you'll go and get the next instruction. So half of your instructions are spent getting the instructions. Half of the cycles are spent getting the next instruction. So by just solving that problem and making those work in parallel, we can do something useful every cycle, because we're always getting the next instruction at the time you're running the current one. When the load of laundry is running in the washing machine, you're already telling the next person, bring your basket to the table. You don't wait until it's done to go and do that. So lots of parallelism. Registers, there's only 32 registers. Most systems, some have 64, but we've taken this and done this to CPU speed over the last 40 years. We have not done that to the number of registers. The number of registers has kind of gone like this. It's stayed at around 32. You don't need more than that. That's the lesson, obvious conclusion from that. So if we have 32 registers, how many bits did we set aside in our MIPS instructions? to encode which register, which of those 32 registers you were talking about. If you remember when you did add, and you said add into T0, T1, and T2, and so you built your 32-bit MIPS instruction, and the first 6 bits are the opcode, which is all zeros, and the function code told you that it was an add over here, but you had some space for the destination register and the source registers. How many bits wide are these? 5. You see the relationship? 5, 2 to the 5th is 32. You give me 5 bits, and you can point to 32 different things, because they can each have their own combination of those 5 bits. Can't do 33, but you can do 32. So 5 bits also is really great because it doesn't use very much of my instruction space, and it reserves for the rest of the space for other things. So I'm very happy that it's only 32, because if you kept growing that like you did, the whole instruction would just be like for one register. All right, so that's register memory, and then you have your ALU, which is the center of the universe. This is why we build these things, and then you have RAM. So those are the basic building block components. What I want to do is add some things that some of you may have already sort of surmised, like how does this work? So let's go back up to the program counter, and let me ask you a question. I have to click here first. There we go. So here's my program counter. And if I have a branch command, then I don't want to just run the next instruction. If the branch turns out to be true, I want to modify what's in the program counter up or down some number of lines. And that I-type instruction that I use gives me 16 bits to say how many lines up or down. That's actually 32,000 lines. So you can jump a long way or branch a long way with that instruction. So that's one possibility. You've given me a branch instruction. You've told me how many lines of code up or down from where you are you'd like to go. I calculate it, and I change the program counter to that. The other possibility is that you're not doing that, that it's just a normal other type of instruction, and all you want is just to run the next line of code. Well, that's what the program counter is normally doing. So one of those gets done here. The other one, the branch one, gets done here. You take a value out of the instruction, the constant, you add it to the current value of the program counter, you subtract 1 because you've already added 1. That's one possibility. So this is the branch, and this one is the normal. We'll call it normal operation. How do you pick which one wins? How do you pick which one is actually sent to the program counter? You need something called a multiplexer. And I know that a lot of you haven't heard that term before. Multiplexer, just think multi-selector. So anytime you have a system that has multiple inputs and you choose one of them to pass along, that's a multiplexer. So at the airport, if the TSA agent has 3 lines and he says next from the elite line, next from the regular line, he's a multiplexer. If you have a Coke machine or a refrigerator at the 7-Eleven with 5 things and you reach in and you grab one, you're the multiplexer. You're choosing one output. And they're used all the time in systems as well. So in this case, we need to tell the multiplexer what to do. Now, we can't ask the multiplexer, hey, keep your eye open for branch instructions, and if you see one, send this value instead of this one. There's no smarts in this. The only thing, you've built this chip, and I've told you guys this before, it's a rock. You understand? It's molecules of solids. There's no smarts. There's no program that it can run. It's made out of sand. It's silicon. It's a rock. So the only thing you can do is you stick an electrical charge in, and you've carefully etched little valleys in this rock that allow current to flow. So you chemically created metal paths where electrons can flow, and just like with the electric company, they flow over all the available paths at once. Anybody doesn't believe it, you can stick a screwdriver into any light socket in Houston and you will get electrocuted just the same in all of them. Because the electrons flow over all the metal paths simultaneously unless you do something to stop it. Like with a light switch, for example, or you unplug something, you break the metal path. So we build this stuff out of silicon because one of the tricks that you can pull by chemically altering what's happening on this rock is if you apply a voltage to the side of an element, you can either make it a switch that's on or off. You can change it from being a resistor to a conductor, from a stop to a go. And we figured out how to add little dots of molecules and boil it into the silicon, and it changes the property of the sand. Some things can be convinced. You are normally a resistor, right? But if you insist, if you're wearing leather shoes, anybody ever see a guy come to school that makes a girl's hair stand up with a Van de Graaff generator with a static? You know, you've seen that stuff, right? But she doesn't get electrocuted. Why? Because she's not grounded. She's isolated from ground. So normally, if you reach up and you touch something that's electrified, and as long as you're wearing rubber shoes that don't create a ground, or you're not touching something else that's grounded, you will not get electrocuted by it. But if you insist, you will. I had an uncle, God rest his soul, that worked for Oklahoma Gas and Electric, and along with his supervisor, we're working a 100,000 kilovolt line right out of the power plant, and somebody turned it on. Killed them, eventually. They were wearing all kinds of protective insulating gear and everything else. If you insist, you can be a conductor. All right, so we can turn you from one to the other, and you can turn bits of this from one to the other as well. All right, so family was taken care of, though, so that part was good. So you've got instruction memory registers, and then you have this MUX. So how do you tell the MUX which one to be? Well, first you need to know that it's a branch instruction. So let's say there's branch instructions, and I have a 6-digit opcode. Anybody have the MITS reference guide handy? Let's just make something up and say all branch commands have a 0 and a 1 as the second and third bit of the opcode. And you guys can tell me different if you can spot the pattern. It'll show you in hex, but maybe you guys can see it. So what I want to do is change what this MUX does from letting this go through to letting the other one go through if it's a branch command. So can I build a circuit to do this? So what this shows is I put an AND gate up here, and I want to know two things. First, that it's a branch, and second, that your 0 test failed. That when you ran your, let's say, branch equal, T0 and T1, you remember how branch equal works? You have a branch equal. I want you to test these two variables, S0 and S1, or I'll make the other one 0 just to make it fun. And I want you to put the result here. The result is either going to be true or false, because this is a test and not of the emergency broadcast system. So if it's true, this will be a 1. If it's false, it'll be a 0. So if it's a branch command and it's not a 0, then it means this was true, and you're supposed to take the branch. So this will come out as a 1 because it's not a 0. And I also want to know if it's a branch command, because sometimes things aren't 0 because they're just not. They're just math commands. So if both of those things are true, then I want you to tell the MUX to let this guy go through. So it'll start a voltage and it'll change the property and it'll let this become a conductor and it'll go through. So if I take a knot of this and I AND it with the output, then this will be 1 only when these two bits are this pattern. And if those two bits are what all branch commands have in common, then I can use the opcode itself and run it to an AND gate. So that's why it can only be a rock and still perform the calculation. It changes what that MUX does. By sending a positive signal here, it electrically makes it into a conductor, and it makes this one into a resistor. So it reverses it. It's all done molecularly. There's no swinging gate, there's no switch, there's nothing like that. You're just changing properties by adding or removing a current from it. So people got pretty excited when they discovered they could do this. It was pretty neat stuff. You have a MUX here to figure out what am I going to store back in the register as a result? Something that came out of memory, like with the load word command, or something that came out of an ALU, like a math command. So there's a MUX for that. There's a MUX here to decide for the second operator that goes into the ALU, if there is even a second operator. Not, for example, only has 1. It's a unary operator. But most of the rest of the commands have 2. You know, you're going to add a number to something. Some commands let you specify it as a constant. So how do I know when I'm supposed to pull it out? Well, if it's an R-type instruction, your second thing comes out of a register. If it's an I-type instruction, your second item, comes out of the instruction. It's a constant. So here's a path that can take. Here's the path of register. There's a mux that decides which one goes through. So if you will help me figure out what the unique combination of opcode bits that I can always count on separating R-type and I-type instructions, I can build a little circuit and make that mux work. So we've already learned enough circuit design, even in this class, with just 2 or 3 elements to start to put this thing together. The only problem is there's billions of them. That's the problem. If you feed a circuit design or an algebraic equation to one of these programs that do chip design, it'll crank out a design for you. It'll crank out a circuit. Or if you feed it the circuit, it'll build a truth table then you can use to make sure it's working properly. It'll tell you what your clock speed is going to be by counting the number of gates. You tell it what chemistry you're using. It knows how long it takes for the chemistry to change, blah, blah, blah. So we're off to the races on that. Okay, so there's that control ball in there that you saw, that all those blue lines are going to be used for control signals. So let's get to logic design conventions. An element that combines things together and gives you a result is simply a combinational element. It can be a single AND gate, or it can be the ALU in its entirety. They're both doing the same thing of taking 2 inputs and giving you 1 output. So it depends on your point of view. A state element is something that remembers the state of things, better known as memory. RAM is an example of memory. So have you guys had any electronics before this class? Do you guys know what a capacitor is? A few people? Okay. So a capacitor is something that will store electrons for a moment. And you can accumulate electrons, you can accumulate a charge in a capacitor, and then dump it all out at once and get the sum of all of the inputs. So this would be like pouring a cup of water at a time in one of those big giant tanks in the desert in the old Western movies with a steam locomotive engine, and like, because you have a little windmill and it's just pumping a little tiny little amount of water, and then the steam engine comes up and dumps the whole thing into the boiler and then continues on the road. So it's stored that stuff up. That's like a capacitor. In fact, they use water tanks all the time to teach the way capacitors work. When you have an RFID card that you use to tap to pay, or in your vehicle to go through a toll tag, as you get close, you have a collector antenna that is collecting power from, if it's passive, it doesn't have a battery in it, it's collecting power from an emitter, and it's storing in a capacitor, and as soon as it has enough, it discharges it into the circuitry inside that card, and it's enough to run through gates that will pull your serial number and power an antenna and broadcast that pattern, and that's how they know it's your car. Right? You don't need a battery. It uses a capacitor. So it's just collecting energy all the time. So in this example, the way memory will work is you tell it to remember a 1 or a 0 by storing a high voltage or a low voltage. And when you ask it later, what was it, it will show you a high voltage or a low voltage, and you will conclude that it was a 1 or a 0 correspondingly. Here's the problem. Just like water tanks in the desert, capacitors leak. And if you let it sit there for a moment, it's going to forget. The charge will drain out anyway, whether it's all at once like you wanted or not. So you have to remind it periodically. And with RAM elements will remember what you told them for somewhere between 1/100th and 1/8000th of a second. So that means somewhere between 100 and thousands of times a second, you tell the CPU, just a moment, your RAM is not available for loads and stores, which is why you bought it, and a significant portion of the time, it's busy going around and asking people, what was it I asked you to remember? 1? Oh, that's right. Please continue to remember it. So you will dump and recharge the capacitor. Because if you don't do it, the person says, well, I remember it was a 1. Yeah, but you were just about to forget. Because if I waited any longer and I came and asked you what it was, you were going to show me a voltage that makes me nervous. Is that like a weak 1 or a strong 0? Like what value was it? And you don't know. You can't conclude. So you have to constantly refresh RAM. Other types of memory you don't, like BIOS. If you ever updated the BIOS on your system, turn the thing off, you turn it on again the next day, the program's still there. The memory still remembers it. So those are state elements. So you have combinational and state elements. Sometimes people call them combinatorial. This is not the point of this question, but I just happened to notice there's a little truth table here. It's a circuit that has 2 inputs and 1 output. Can anybody tell me the algebraic equation that this circuit implements? Is it an OR? What about the third row? Is it an OR? How about if I told you it's this, B? That's all it is. I don't know why they chose that. It's just B. So if you asked me to design a circuit, I would work very hard while shopping and charge you $5 for a very sophisticated circuit that had a wire coming in and a wire going out. And let's say this was A and this was B, and I would run a wire here and then cover it up with black plastic and sell it to you for $5. That's the circuit you would need to do that. And you could build it out of anything. You could build it out of copper if you wanted to. So it's kind of funny sometimes, the examples they use in the books. It made me laugh. That was a little unfair, but funny, hopefully. Maybe more for me than you, I guess. But okay, clocking. Remember we talked about clocks. And we have a little crystal that when subjected to a charge, it doesn't change from a resistor to a conductor. What this little guy does is oscillates, vibrates. So you can actually observe the charge that comes out, and the charge is sinusoidal. And the time between peaks is directly proportional to the size of the crystal. So if you make a crystal a certain size, it will oscillate at a certain speed. So once you figure out what the slowest path is through your CPU and you know the clock speed you want, somebody will build a crystal that size. Well, they're all mass-produced at a huge range of speeds, and you just order and they ship them to you pre-made already. But this is hard to do. So what we want to use this clock for is to get everybody kind of in sync. When is it time for the PC to hand the address to the instruction memory? When is it time for the instruction memory to hand it to those 5-bit identifiers to the register memory? When is it time for that ALU to add 4 and to spit its output out? You know, these things don't all happen in the same speed because some of them have to go longer journeys to get there. So to make it not debatable, like where in here, we try to make it a little more obvious. So we turn this, and this should match up, but it doesn't. Anybody know what this type of signal is called? Square wave. And if I zoom into it, it's not really instantaneous. As the picoseconds go by, it needs a few to climb. But what everybody's watching for is the change here. And when this change happens, that's when they begin the next step, or they release the results, or whatever the task might be at hand. So what you've got to make sure of, and this is called edge-triggered clocking, where things are going to happen based on the edge. Some systems will also do more things on the falling edge, but in our example, we have a rising edge clock-triggered system. So things only happen when it goes from low to high. When it goes from high to low, we don't care. So you've got some time, right? Time passes in here between this point and this point. So anything you need to get done, you have that long to do it. So if you ask a memory element, when it sees the rising edge, to dump its contents onto an input pin, that's a path that goes through 1,000 semiconductor elements, blah, 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 combines with lots of others. You better be done by the time the next rising edge, which let's say is over here, because you don't have any longer than that. When the next rising edge happens, this memory is going to take whatever the voltage is here and store it and remember it. So that's how long you have to get something done. So you've got to pick a clock, a crystal size that gives you a clock speed that's slow enough to make sure things get done. So this is a little bit like a maze, and you guys have all seen these before. You turn a mouse loose and you put some blocks in, and change the path around, and you see how long it takes to get to the cheese. And that's the reward. And there's lots of dead ends, Maybe there's millions of possibilities and only one right answer. There's only one correct path. And so you want to see how long it takes the mouse to do it. So circuit design is a variation of that. Think about it like with electricity. You have a million mice. Each one is assigned one of the unique paths. So this is like a tree now, right? Nodes on trees. Each one is aiming for a different leaf on the tree. They all go at the same time because electricity goes everywhere there's metal all at once. So any place chemically where you've built these traces, it'll go until it reaches a roadblock, a resistor. So this is like a million mice that are turned loose, and as soon as they hit a roadblock, they vanish. And eventually, after a moment or so, you're only going to have one mouse left, and he can do tricks. He can go through little tubes, he can run over wheels, he can splash through water, and you can have your electrons do tricks. They can go through AND gates and OR gates and NOT gates and whatever chemically you've asked them to do, and it'll eventually make its way to the end and get the cheese. Yeah.
So all the knowing go through all the state spaces like the or will be like
No, they'll go through everything they can unless you've resisted them away, unless you've crimped it with a resistor. You have to have enough electricity in your power supply to run all those in parallel. Right? Every single path on the chip, that's the sum of all the links of all the paths, that's a lot of current. That's why they get hot. Right? Because every one of those creates heat because there's resistance. So you may have a million of those at a time that are being run, and they generate a lot of heat. That's also why we make them out of rock, so they don't melt. So it's really hard to melt a chip. You have to basically get to the temperature to melt glass, more or less. Okay, so that's what's happening here. I'm going to show it to you in a little different version. Where did I have it? Where does my 401 go? Did I lose it? Must be this one. I must just not remember. No, it's on the next page. That's where it is. I remember now. So you have a state element, rising clock edge. It dumps its output. Nothing tells the combinational logic that it's time to start calculating. It's constantly calculating. It's always receiving some kind of current, maybe low, and if there's enough current, it will change its state. It will change properties from a conductor to a resistor or not. But it's always doing it. Nobody tells the combinator. As soon as you release voltage, it's racing through as fast as it can. So the only thing the clock's going to do is tell the state element it's time to dump the right voltage onto this circuit. And it passes through as fast as it can, and it's waiting at the end. And when you're sure you've given it enough time and there's another rising edge, you say it's time to record the voltage on that wire. And that's the output pin. So none of this in the middle has to worry about clock. It goes at light speed. It's constantly calculating. The only thing you're really clocking is when do I put inputs in that are valuable to me, and when do I pull outputs out that are valuable to me. But it's a continuous circuit. It's constantly calculating. All right, so you use these as a control signal, and you say it's asserted if it's a 1, it's deasserted if it's a 0. Please don't call it desert or deserted or deserted. It's deasserted. So you may have to practice that a little bit. All right, so it's another example of the same thing there. And again, they hide it. So to build this up into a data path, this is basically a combination of elements that we're going to put together. And I'm going to skip past the building blocks and basically show you with a couple of animations and then some sketches sort of what's going on. So here's my program counter, and I need to start it off here. So it has 500 in its memory, so it's going to hand that address. That's the address of the next instruction. It's going to hand it into instruction memory, and it'll get passed in. Great. And the instruction memory will go grab the contents, and we're off to the races. But that's not the only place it goes, right? It also goes in parallel because there's another wire there that kind of leaves and goes up that you can see here. So the copy of it also goes to this adder, which is nothing more than some of these gates and circuits, and it adds 4. How do you add 4 to something? Well, you hook up the right elements that mean 4 directly to the power supply. So they're always asserted. You know, if that's the way the thing works, it never does anything else. So it's just hooked directly up to the power supply. 5 volts, you know, whatever the voltage is, straight into that element, always at all times. So your chip always has to have those voltages available. All right, and then it's going to add, and 504 is going to come out of that, and it'll be ready when the clock signal says. It'll grab that value and pull it into the PC, and when the clock signal says, it will hand it to the instruction memory. So that's basically the idea. Registers are not RAM. Registers are a different set of 32 elements. So not surprisingly, there's only 5 bits needed. We talked about that. So if you feed 00111 into the register, that's enough to select among 32. It's a mux, a 32 by 1 mux. It will let the value of exactly one register, the one you chose, to flow out through this set of wires. And out of the other one comes whatever register number you fed here. And it looks like the value here is 488. I don't know why it's so faded. I probably should just run the animation. And if you need a third register, a place to store your result, there's room in here to feed up to 3. If there's data that's coming back that you need to store in the register at the end, here's a place for the data to get back in, and you write it to that one. So not all commands use all these. So you have to kind of use some control signals to block some of these things off. And then you'll use control signals to also tell the ALU which of 16 things it's doing. Only 16 things. CPUs does other things that don't need the ALU, like storing memory and things like that, but there's only 16 classes of instructions, so I only need 4 control bits. 4 control bits. So maybe I can pull those out of opcodes. Maybe I could build a little circuit to do that, like a little lookup table that's built out of rock. We have a sign extender. We all know what sign extension is. There's branches. Branches are unusual because branches are tests. They're going to test to see if 2 things meet the condition. One of them has to be calculated in the immediately preceding instruction. That's a rule for branch. You do your comparison, like you do your subtraction or whatever, and then you run the branch. And the reason why you need to make it the preceding one is because branch is going to use the 0 wire out of the ALU to tell whether the branch result succeeded or not. And the ALU is only going to have the value for the instruction you just ran, not the one 5 instructions ago. So you have the AL value that comes out, and this is a stall. It requires a stall because the branch can't know what line of code to run until it has the result out of the ALU. And the ALU is not done with its answer yet. So there's a delay. It's a delay target, and it's a problem in most computers. So what systems will do is they can do one of 2 things. They either wait 1 cycle to let the preceding equation make its way through so we know the answer. Goes a little further through the pipeline. This is like you got to wait till the end to see if there were genes in the first load of clothes, that analogy I use. Or you, and if you're going to do that, if you're going to stall, there's a special instruction, or you guess which one's going to be next. So let's take those one at a time. If it's something you're not supposed to do at all, there's actually an instruction in every assembly language architecture that means do nothing. And you can add it as a line of assembly code. It can take up 100 lines, or 1 line, 2 lines. If you need the system to just continue doing nothing, then when the clock signal starts, it'll pass a 0. It'll flow through the combinational logic. The next one starts. It pulls it out. That's a no-op or a NOP. And you may have run into those, before. It can also be used as an insult, by the way, just to sort of start inculcating you with some nerd humor. Like, you can say, like, he's 404, man. Get it? Right? So that used to be an insult in the early days of HTTP. You can say somebody's a no-op. You can define that however you want. There's endless possibilities. You don't want to be one, though. I'm pretty sure of that. So you can have that in there. So you can give the preceding instruction a chance to work its way through the chip so you know what the answer is, and then know whether the branch succeeds or not, or you guess. And we guess. In MIPS, it guesses. It will just run the next instruction that the program counter is already pointing to, and it will fetch it from instruction memory. It will decode it. It will hand it to the register file. It will pull the values out. As long, it can even go through the ALU. All of that's harmless. As soon as you write to memory or write to a register, you've crossed a point that there's no Control Z on the chip. You can't undo. So you can guess the lines of code to run and make some progress as long as you don't get past a point where you have to write, which is why in most pipelines the writing happens at the end. So you have a chance to do that. So this would be like somebody coming to the restaurant. They're a great business customer. They always bring their client, and they always want to show off. So they always order either this chocolate souffle or baked Alaskan for dessert, and they each take 20 minutes, 30 minutes to make. And you know they're in a hurry, usually. They don't want to wait 20 minutes. Or the client will say, you know, I really don't have time, and then you lose the sale because it's your most expensive dessert. So what are you going to do? When they come in, you're going to guess, and you're going to make the one that you think they're going to want. If you guess wrong, it's no longer wait than it would have been had you not asked at all. But if you guess right, you've sped things up. So that's, think about baked Alaskan and chocolate souffle. Everybody likes that, right? So you won't forget. All right. So if you see a question on it, now you remember dessert. All right. Whatever it takes, guys. You know, whatever example it takes to get it done. So you have some control lines in here. One of the things the sign extender needs to do is be shifted left so it turns word numbers into byte numbers. That was your 9 versus 36 comment earlier. Here's where that's done, you know, right here. So if we want to build up a single data path, we can start adding muxes back to this thing, and we can eventually work our way up to this. And this is the end of our lecture. As soon as I draw you 2 highlighted examples to prove to you that what we have so far can do a variety of types of instructions already. So we're actually way far along. Let me ask you guys, at the beginning of this course, did anybody ever think they'd be able to look at a diagram like this and have any idea what in the world was going on? You do now, right? I mean, you have an idea. You're getting there. Yeah, nice. All new knowledge. So program counter comes in, reads an instruction. We see that it's an R-type instruction. We tell the register memory the 2 places we want to pull from. We also go ahead and tell it the register we're going to write to later. The muxes are signals such that these 2 signals make their way into the ALU. The ALU performs whatever the instruction says to do, signaled by the 4 control bits here. If it's a 0, that's something that we share, but the result comes out. And in this case, it's not a store word, so it doesn't need to go to RAM. R-type instructions do not go to memory. I-type instructions are required if you need to go to memory. So we're going to bypass this and tell the mux, pick me. And he will pass the result back into the register where it knows where you want to write it. So that's the way it works with an R-type instruction. Let's try it with an I-type instruction. You come in and you read, you see it's an I-type. One of the things you're going to have is an immediate that needs to be sign extended and given to the mux. The other thing you're going to have is a register that you need to read from. Take me to 12 bytes past the start of my array. The start of the array is in register S0. So add 12 to that for me, and that's where I want you to store this register. So you're going to tell it where you need to put stuff. It's going to calculate, pass the answer along, and there's data perhaps in there in some other instructions, but basically you're giving the address, and because what you're trying to write with that instruction, and let me switch back so I can write the instruction out for you so I don't totally lose you guys. If we're going to store word, the value of T1, I want it to go to a location that is 12 words past or 12 bytes past the start of my array in S0. This is S0, and this is 12, but down here is T1, let's say. So it's going to remember T1, so it will take the contents, in this case, of T1, because it's store word, and dump it out here, and that's the data that should be written to memory. And this tells it the address where to write it. And when it's done, there's nothing for the mux to do. If it was a load word, on the other hand, it would be a little bit different. I would give it the address, and I would tell it to read the data. That would pass back, and that T1 would be used by this guy. This is where I want you to store what you got out of RAM. Store it into T1. So that's a load word. instead of a scoreboard. So, you know, we're getting there. There's more to come. One of the things we're going to look at is simple logic formulas, simple algebraic formulas that I can build with a circuit in my control module, which has disappeared again from this diagram, that will control every element on the chip perfectly based on opcodes and things like that. You can actually write, it's a lot easier than you think, much shorter than you think. It'll fit on like half a page of all the instructions you need. And those instructions examine the opcodes and tell every element on the chip what it needs to do. And it passes through. And magic. All right, guys, I'll see you on WebEx on Thursday. You have a homework, hopefully fun. It's 10 pages long, so you know me, lots of pictures and lots of explanations. I try to walk you through things step by step by step, which the book never does. The animations kind of do, but you know, they're sort of like, define the universe, give 3 examples. Really? Can I have a little something to go on? Nope. And when I look at the answer guide, it says 5. Thank you very little. Doesn't give me any detail at all. So I just rewrite all of them myself, and that's why they're long. Hopefully it doesn't kill you, but it'll take you a few hours, I think. You're going to be burning up, you know, your group chat, probably. So, all right, have a great one. See you on Thursday. Have the chapter wrapped up by the weekend. We're going to be well into chapter 4, so don't fall behind on that. All right, see you guys. Sorry about the audio, guys. Let me stop the meeting and quit out of this.